Okay, good afternoon and welcome to all the course coordinators and course participants under the 85th program of IRS in the outreach category, that is on the basics of remote sensing, GIS and GNSS, as well as the course participants for the 87th course on the global navigation satellite system. So for the module 2 and for the 87th program, today is the first day. So first we will brief what are the lectures which are going to take place under the series on global navigation satellite system. This program will run from 13th September to 24th September, and it will include the following lectures as it is shown on the slide. So we will have introduction to GPS and GNSS. Then we will discuss the various GPS receivers, accuracies. Then the satellite-based augmentation systems we will discuss. We will discuss the Gagan system. We will discuss the Indian regional navigation satellite system. What are the GPS signal characteristics that we will be covering? We will have a recorded demonstration of differential GPS also. And then for the processing, we will have an advanced lecture on the GNSS. Mobile mapping will also be there, that will be covered in basically under the GIS series, something we will cover in this course also. So let us begin the first lecture in this series on the introduction part. So let us discuss about the requirement of the GPS. What was the requirement and how it has evolved actually. Okay, so the humankind, they have a very basic requirement of origin and destination from the very beginning and the development of civilization itself. Okay, so human beings themselves, they are driven by the maps because they are on the move and they do have to return to their origin places also. Being a social being and having a family, so for various purposes the man moves from one place to another place and then they have to return to. Okay, so in the initial case, what we can understand is that thousands of years back we have been using basically the mental maps. So we have a picture of the surroundings and accordingly the movement used to take place. So they used to run behind the animal for the purpose of food, and maybe after kill they have to return back also. So we have observed that in the various civilizations like the Indus Valley civilizations, Babylonians, Egyptians, Greeks and Romans, when we have investigated as per the archaeological department requirements, we have found that very good maps or very good laid out cities have been there earlier with very good ventilation systems, perfect 90-degree angles for the roads and good drainages. Okay, so what we have understood here is that we have certain requirements, and that requirement is basically about the surveying and the mapping. So in surveying, actually we have studied in various courses that we have very simple instruments like the chain, tape, cross staff, optical square, theodolite, then tachymeters are there, compass are there, various types of levels are there, electronic distance measurement equipments are there, and then the total station. So these we have studied in our various courses in geography, geology, civil engineering, some practicals in agriculture, and our day-to-day life also. Okay, many times we are observing that people or the engineers, they are using total station and other equipments while constructing the roads or the buildings which we come across which are under construction. So we have seen many of these equipments that they are being under use. So in the series of these equipments only, basically the global positioning system is also a surveying equipment only. However, we forget it because it is actually working in tandem with various other technologies like internet, various softwares which are there So it is a full package actually. We can call it a GIS package actually, where GPS is one of the important input. And GPS gives us basically the location, that is the latitude, longitude, and height of a place. And that was the basic purpose of the surveying. So GPS does is a surveying equipment only. However, it is a very useful equipment and is compatible with many technologies wherein it can give the inputs for various type of modelings or preparation of maps or running various GIS algorithms. So GPS is one of the important input into that. Like as we do in the surveying, in case of GPS also, we are doing the triangulation or the trilateration. Okay, these are the techniques which are extensively used in the 19th and 20th century while doing surveys at local scale or countrywide scales. So in case of GPS also, primarily we are performing the trilateration technique because we are mainly dealing with the angles, with the distances only in the case of GPS. Primarily distances are having more importance in case of GPS. However, everything we distribute in terms of errors and triangulation also becomes part of that. Okay, but when we are locating a position, that time trilateration is the major surveying technique which is being used, and we will discuss that. How it has happened basically? What has happened is that we have launched the first satellite, that is Sputnik 1, in October 1957. So Soviet Union that time, they have been successful in launching the Sputnik, and the challenge they faced was to locate the Sputnik into their orbit. And that challenge has been met with the Doppler techniques. Okay, so the Doppler shift techniques are used for locating the satellites in their orbits, and the requirement for Doppler shift measurements is that the ground position need to be known. So, and that was known. Okay, what was unknown? Unknown was the position of the Sputnik in the space. So we can say the known was on the ground, that is the location of our station, and the unknown was the satellite in the space. Thereafter, Sputnik 2 was launched in November, and then the Explorer series of satellites were launched by USA. Gradually, the data has been accumulated, and it is found that the data, orbital data, was very much useful for making the shape of the Earth also. So based on that, the Earth flattening ratios were also computed using the satellite-based data. So that was something which was not planned earlier. So primarily the option was to launch the Sputnik or the Explorer series of satellites. However, later developments, we have found that these computations which we are doing for orbital mechanics, they are useful for the measurement of shape of the Earth also. And then various geoid models also came into being, and one of them is the geoid 90, which was extensively used for the NAD83 datum, which was again extensively used for various mapping exercises. So this is North American datum, and that was quite famous in its time and utilized in its time. And then the entire computations are also very important, and we need to distribute various types of errors. So lambda technique was also introduced in 1993 for the least square ambiguity decorrelation adjustment. Thereafter, what we have seen in the due course, various type of equipments have also developed. So from the very basic landmark based navigation which we have been doing earlier thousands of years back, by markings on the stones or the trees or some kind of monumentation, and then thereafter the progress of this origin destination or computation or having an idea of our own location on the earth was based on the celestial navigation. So celestial navigation also played very important role in this journey of the development of GPS or the surveying primarily. So the latitude was computed very accurately, whereas the longitude was having certain issues as per the celestial navigation systems, because it requires accurate clock. So till 17th century, the accurate positioning, having a correct measurement for longitude was a big challenge. So based on the sun in the daytime and in the night time, based on the moon and the stars, also a lot of navigation has been done in earlier times. And even today also we do use all these things still. So we have various type of star sensors on our satellites. So they are also using some sort of celestial information which is there, different type of constellation of stars are there. So they are still being used in various ways. What we can say is astronomy is also largely being used in our remote sensing science. The magnetic compass has come, gyro compass was developed, then the radio direction finding, radar and inertial navigation system. So these were various systems which has helped us in navigation over time. And then a time came when we had a very important development, that is the long range navigation. LORAN A by the US Navy, Air Force and Army, turn by turn it has been switched between their hands. And this LORAN A system was a tower based system as we see our mobile towers today. So these long range navigation, these are very tall towers. So few towers across the large land masses helps in the navigation on the land as well as in the ocean. And this LORAN ABC, they have been also been utilized for paid services for the commercial navigation. So LORAN C is still functioning and providing services for the strategic agencies as well as for the commercial shipping industry. Similarly, Russia has developed the Chaika system. So Russia has developed Chaika system and the US has developed the LORAN C system. Now they were developed initially based on the Cold War era requirements. So they are not global systems. However, they cover the area of interest of that time as per their requirements for the US and the Russia. Once this LORAN C and Chaika were developed, which were regional in category, we can say, the global category systems were also developed, like the Omega by USA and Alpha by Russia. They were again tower-based systems. So these are basically terrestrial-based navigation systems which can assist someone in the navigation all over the globe. So Omega and Alpha systems were there earlier as a terrestrial navigation-based systems. So they were functioning in the 1960s, and LORAN C, as I told you, it is still functioning in different modernized way, like the E differential LORAN, so which is capable of giving very high accuracies of the order of few meters. Then in 1980s or in 1978, the first satellite under the GPS category or the Navistar GPS category was launched by USA. And for the global satellite-based navigation system, the initial operational capability was announced on 8th December 1993. Okay. At the same time in 1993, almost parallel to the development in US, the Russians also developed the GLONASS system. So they are announced their initial operational capability, that is IOC, in 1993. After thorough checking in 1995, the full operational capability was declared for GPS by US and the GLONASS by Russia. So here also the developments were parallel between US and Russia. The International Geodesy Services, which later got renamed as International GPS Service, and now it is International GNSS Service. So this too started functioning in 1994, and with the closure of the Cold War era, the US and Russia came together and started talking about more development, and they started sharing code in the CDMA format. So in the 2006 time frame, the concept of global navigation satellite system was developed. So earlier, what was the case that if you want to use the Navistar GPS signals, you used to have one receiver, and for using the GLONASS services, we used to have second receiver. Okay, like if you want to use BSNL service or Airtel service, earlier we used to have two mobiles because single SIM mobiles were only there. But later today we have dual SIM mobiles. So in the same mobile we can have the BSNL SIM or the Airtel SIM also. So similarly, in 2006, this combination occurred in an analogous way for the GNSS, where in the single receiver vendor were able to develop a hardware which works on the GPS as well as GLONASS combinedly, not only in terms of hardware but also in terms of the software solution also. So that is the thing which developed in 2006, and it is a system of systems, what we call, or the constellation of constellations, because one constellation belongs to the GPS, another constellation of satellites belongs to the GLONASS. So we are using them jointly for the positioning or the navigation problem solution. Okay. Thereafter, in 2000, actually what happened when the satellite-based navigation started, initially it was thought that the terrestrial systems become redundant, but then it was understood very soon because of other international developments that we cannot depend 100% on the satellite-based navigation systems also. So that started the development of the Lorentz system again, which was otherwise in the dismantlement stage actually. Many of the towers got dismantled also, thinking that satellite navigation will be a better option. But now in the 2000 onwards scenario, it was very clearly understood that we are going to need terrestrial-based navigation systems as well as the satellite-based navigation systems also. So in 2010 onward scenario, the concept of integrated receivers also came into being, where now we have a chip which is capable of providing the satellite-based navigation solution using the GNSS, as well as the terrestrial-based navigation solution using the eLORAN or the eChika. So this is from the Electronica company. It is LORAN D++. Okay, there is 6 centimeter integrated chip for combined satellite-based and terrestrial-based solution. Then after the disintegration of Russia, actually we saw that GLONASS have not been functioning fully, and gradually it recovered, and in 2010 again it resumes its complete services. And during this time frame, the Japan also started developing the quasi-zenith satellite system. And then in 2013 to 16 time frame, the Indian regional navigation system, IIRS, Indian Regional Navigation Satellite System, was also developed. It is known as NAVIC system, as named by our Honorable Prime Minister. So this also gets fully developed in 2016. Now currently, all its signals are fully certified by the international agencies for use of any purpose. In the ocean applications, it can be used for the mobile telephony, in the smartphones. So these all signals from IIRS are also certified. So what we have seen is that GPS GLONASS are fully functional, whereas BEIDO, which is a Chinese-based global navigation satellite system, it also got completed in 2020. Now, besides these three systems, GPS, GLONASS, and BEIDO, there is fourth system which is called the Galileo. It is also under development. And this Galileo system will also be fully functional by this year or next year. So we will have 4 fully operational systems in the times to come, and GNSS is going to play more and more important role in the times. So now this is a eLORAN system concept which is shown here, and this is a tower-based, terrestrial-based based system, and these are the different footprints for the LORAN coverage. Besides the ocean regions, these are the places where the LORAN sea towers are there. You can see these are quite few in number only, but they provide service in the larger regions. And this practically shows that how the satellite-based navigation system is merged with the tower-based system, and provides a joint solution of satellite-based and terrestrial-based navigation system. Then recent development, I'm trying to bring you to the latest developments, and then we will go to the details of the basics for each. And then there is a lot of development in the smartphones also. So in recently Xiaomi Mi 8 also came, where the smartphone is capable of receiving the raw data also for the GPS signals, and it can compute the position within the mobile itself. Okay, so it is not an assisted GPS, but it is a GPS within the mobile and capable of dual frequency GNSS functions. So that is the thing, that from complex equipments, the technology is transferring to the handheld smartphones. Similarly, the Navic has also come in the smartphone, the Qualcomm Snapdragon 720 chip, and beyond that, the chips have been developed and they are available in mobiles for the Navic, that is the Indian system-based applications too. These are quite important for the software developers because they can develop various apps over that. Then there is a service called Eurofix for the European region, where again this Eurofix provides the position to the users based on the terrestrial-based navigation system as well as the satellite-based navigation system. IIT Bombay has also developed a miniaturized chip for the utilization in various equipments under a program which is sponsored or funded by Ministry of Electronics and Information Technology with SAMEER, that is Society for Applied Microwave Electronics Engineering and Research. So this chip has also been developed by IIT Bombay. And then you might have seen that Map My India, that is also in good collaboration with the government departments now, and they have also come up with a mobile based application using the IIRS signals. So that is how I have tried to take you from the historical development till today's advanced scenario. Now we will go deep into the developments, how they have happened. So that is a theoretical component, and then how what are the type of signals and other technical things that also we will cover. So as I have already told you that the Sputnik satellites were tracked using the Doppler shift, wherein the known position was on the ground and the unknown position was of that of the satellite in the space. So at the time, Frank McCurry, who was the chairman of Applied Physics Laboratory at the time, he has given a task to his team that is it possible to do the reverse, or can we inverse the problem? So what was the problem? The initial problem was to locate the satellite in the space. So known was on the ground and unknown was in the space. So what was the new question given by Frank? He told that if we have known locations in the space, is it possible to find out a location on the Earth? So that was being computed by his team, and it was found that it is possible. Based on those computations, the satellites were launched and regional systems were developed. That is the transit satellite-based system. So it was used for Navy also. It is also called the Navy Navigational Satellite System. It was developed in late 1950s, and it was consisting of 6 satellites, and it used to give 2D solutions. So latitude and longitude, we used to compute using it, and it was extensively used by Navy. So because oceanic applications were there for the Navy at that time, the Z can be taken as known as the mean sea level. So this 2D solution merged with the mean sea level provides a good positioning to the Navy. And similar system, which is called cyclone, which means cyclone in the Russian, 10 satellites were launched by Russia also, which actually consisted of a military system called Paras and a commercial or civilian system called Cicada. So these 10 satellites were launched at an elevation of 1,000 kilometers, and they were also providing position. So these two regional navigation satellite systems were also part of the development. Now, based on this, again, as I told you initially, that Earth geoid models were also prepared. So the Smithsonian Astrophysical Observatory, they came up with the standard Earth model based on the various computation of the satellite orbits. And the Goddard Earth model was also developed by the NASA. So in the due course, various Earth geoid models are developed. So you must be aware of EGM 96 or EGM 2008, which we are using nowadays, and they are more frequently used currently. So similar such systems were there earlier. One. So now, as you know that like our Survey of India topo sheet that we have prepared in the Everest ellipsoid system. So globally, there are various ellipsoids which has been used by various countries. Okay, and they do not match with each other because they are the local best fit curves for their region. So now the geodetic datum transformation is also another area where this satellites could contribute. And it became possible to have transformation parameters among various datums and provide an accuracy of plus minus 50 meter in 1970s. So in 1970s, it was a good accuracy for those times. So coming to the satellite navigation again, so currently the scenario is that we are getting an autonomous geospatial positioning by 4 systems, which are intended for global applications. Out of these 3 systems, that is the Navstar GPS, GLONASS, and BEDO, respectively from the USA, Russia, and China, they are complete and they are providing full services. Whereas the 4th system, that is the Galileo, is under development and is going to complete soon. And among the regional category, the Indian Regional Navigation Satellite System and the Quasi-Satellite System are operational from the India and Japan, respectively. So these show various blocks or various generation of GPS satellites, which evolved over time from block 1 to block 3. Then initially the development was for the defense purpose for the GPS. However, because of some international events which took place, especially the accident of Korean Airlines, it forced the President Ronald Reagan basically to support the facility of Navstar GPS for civilian operations also. And thereafter we are getting the GPS signals for the civilian operations also. And GPS is a 6-orbit based system. And GPS is basically intended to provide the position, velocity, and time to the user in a common reference frame. That is the requirement laid down by the US Department of Defense. So position in itself includes the latitude, longitude, and height above the datum. And then the velocity of the receiver is also to be computed, and then the time also, because atomic clocks are there on the Navstar GPS satellites. And these systems are performing much better than the ground-based navigation systems, because on the ground also we have terrestrial systems, but they also suffer from the signal attenuation because of the objects above the ground, like the trees and the buildings. They attenuate the signals in case of the ground-based, tower-based systems. So the satellite-based systems are providing better services globally, and they are forming a major system which is now currently being used by important agencies like the International Civil Aviation Organization, who have also defined the GNSS as a worldwide position and time determination system. Okay, position provides us the latitude, longitude, and height, and the time also is provided along with that. from one or more satellite constellations, that is from the GPS, GLONASS, Galileo, BEDO, or the IIRS or the QZSS, and aircraft receivers are also involved into these services, and the system integrity monitoring systems on the ground. So all these has to support the required navigation performance for intended operation. So this is how the ICAO has a very wide perspective for the GNSS and its application. So currently we have a multi-model systems which is providing services on the earth, in the ocean, and in the space also currently, because the satellites which we are launching, they also have GPS receivers aiding us in the positioning of the satellite. So there are various other things also, like reflectors, star sensors. There is a lot of mechanism to locate the satellite also, but now GPS is also one important such thing. And then there are augmented systems also, which we will discuss in the coming lectures. Now, over the time, we have moved from the time of GPS, GLONASS, BEDO, Galileo to a system called GNSS, which is, we can say, the superset system combining all of these. So what is the advantage with this? So advantage is that a lot of satellites are there now, a lot of signals are there, so we get very good solutions for our applications in terms of positioning, velocity, and time. So we have good dilution of precision factors, indicating good quality of signals and providing us high accuracy for static applications as well as for the real-time kinematic applications. And we are using the phase-based solutions currently, which are capable of providing us the centimeter to millimeter level of accuracies, and the system is very robust and very optimal in costing, and a larger number of applications are now supported. Now let us look at some of the general characteristics of these systems. So we can see this table which has been prepared for comparison. So we are getting the positioning accuracy from various systems of the order of 10 to 20 meters. In velocity, we are getting an accuracy of the order of 10 to 20 centimeters per second. And then in time also, we are getting an accuracy of the order of 0.1 to 0.2 microsecond for various systems. So under the Navistar GPS category, the first satellite was launched in 1978, having PRN code 4. Then Cosmos in 1982 for the GLONASS, G of A for Galileo in 2005, and BEDO 1A was launched in 2000. So like that, these were the first systems contributing to the corresponding constellation of satellites providing the global navigation satellite system. And these all are working with various ellipsoid systems like WGST-4 for the Navistar GPS, Parametry Assembly for GLONASS, Galileo terrestrial reference frame for the Galileo, and the China geodetic coordinate system for the BEDO. So we can see the ellipsoids are also different, but now as all are collaborating, the mathematical differences among them is known, and in the system itself we can choose which system we want to follow. So normally what we are doing is we are using the WGS84 ellipsoid or the datum for our both civilian or strategic applications. So this is a 6-orbit based system wherein 4 satellites are there in each orbit minimum. So minimum 24 satellites are there in the GPS constellation, and this is the BEDO system, which is a bit complex system. It has few satellites in the equatorial plane, in the geostationary orbit, then in the inclined geosynchronous orbits, and in the medium earth orbits also. Whereas the GLONASS and Galileo, they are 3-orbit based systems. So they have 9 to 10 satellites in each orbit, and they are also providing the navigation services to the users. Now this is a table which compares various features of the 4 systems, GLONASS, Galileo, and BEDO. So primarily they are using different type of frequencies and different type of services they are providing. So mainly the frequency which is being used for civilian operations is L1, L2, and L5. there are a few other frequencies also like L3 and L4. In case of GLONASS also L1, L2, L3 are there. In Galileo there are 5 are there. Primarily it is L1, L5 and 6, E5 and L6 actually. And for BDO also there are B1I, B2I and B3I and B1C and B2A. So basically different type of services are there which we will discuss in the due course. Now this naming of some of these constellations is also quite interesting, like the BDO, which is named by China, is also a traditional name, and there in the astronomy also as the Big Dipper. And in the Indian system it is called the Saptarishis. So on that this BDO name has been given for the Chinese system. Then the QZSS also use Mishibiki satellites, which also mean the guide to show the way. And in case of China, in case of India, we are using the Navik, where we intend to say that our earlier ancestors, they were also doing navigation in the oceans using various celestial-based techniques. Now, if we have to understand the satellite-based navigation systems, we divide it into 3 parts. So first is the space segment. In the space segment, we have the satellites. And then there is a second segment which is called the ground segment, which consists of the ground stations, the stations which take care of the satellites post-launch. They update the systems. And the third is the user segment. So we fall in the user segment. So under the block 1, we can say it was the generation 1 GPS satellites. We used to have 11 satellites and they have completed their life. They were launched between 1978 to 85. Then block 2 and 2A were launched between 1989 to 1997. Then block 2R and 2RM, they were launched around 1997 to 2005 and beyond up to 2009. And from the 2009, block 2F was launched. So currently the main backbone of the GPS or the Navistar GPS system is the block 2F, which is providing us the signals in the L1, L2 and L5 carrier waves. Now the current block is the block 3, which is delivering higher accuracy to us with anti-jamming facilities in it. But few satellites are only launched currently. It has become 4 actually, and 4 satellites are contributing to it. And a lot of emphasis on this third block was given to the cyber security. And it is seen that the systems should not be hacked. So about $500 billion are only meant for the software itself. And it is seen that the various frequencies are interoperable between the various GNSS systems like the GPS, GLONASS, Galileo, BDO, IIRS, QZSS. So all have some common frequencies, mainly around L5 frequency. And all these details are given as shown here in this snapshot, that on some given time, you can see that various changes are happening in the details. And currently we can see that the 8 systems for GPS are operational under the block 2R. Block 2RM, 7 systems are operational. In the block 2F, 12 systems are operational. And in block 3, 4 systems are operational. So that is the current scenario. And then we can also observe that because of the development in the science and in the electronics, wherein the weight of the satellites have decreased and the efficiency of the systems have increased, thereby increasing the life of the systems also. So in the initial days, the systems were having a life of about 7.5 years. But the current systems are having a life of about 15 years in case of the Navistar GPS satellites. So now these systems are interoperable and serving all over the globe as per the various satellite-based augmentation systems, also which we will discuss in the due course, with certain common frequencies for the interoperability. Similarly, the Russian system, that is the GLONASS, they also used to have a 3.5 years of life for their satellites. Under the first block, we can say between 1982 to 2005. Then the new series GLONASS M, GLONASS K, and GLONASS K2, which is the currently running category. The life of the systems have increased to about 10 years. Initial GLONASS systems were giving signals in FDMA mode, that is frequency division multiple access. But after the 2006 scenario, when the concept of GNSS was developed, the GLONASS also started giving signals in the CDMA, because the Navistar's GPS system works in the CDMA, code division multiple access system. So the compatibility of the Russian and the US system is developed using the CDMA signal from both of them. Now these are the various details of the GLONASS series of satellites. So starting from GLONASS to GLONASS M, K1, K2, what we have talked, and then thereafter they have a plan for GLONASS 5 and GLONASS KM, as we have the plan of GLONASS. In case of the GPS also, the block 3A and block 3F. So that entire timeline has been made for them, and the atomic clocks are very much used in all these systems. So GLONASS system also works on the central synchronizer, which is based in the ground-based control complex. Okay, and it is using hydrogen measures also, and having an accuracy of the order of 10 to the power minus 40. So that kind of accuracies are there. And basically what is happening in case of GPS also, the rubidium and cesium clocks are used. It is not that one clock is used for any of the systems. There are hundreds of clocks actually. Like in case of Navistar GPS, about 200 clocks all over the globe are functioning. And combining the effect of all of them, our ensembled time is mathematically generated. And that time is finally utilized for all the computation. So it's not that the single clock is giving us the time, but various clocks are there. So in the space segment, we have a estimated $12 billion expenditure in building the GPS initially, and it has a high operational cost also of about $750 million every year and more. So the contract was given initially to the Rockwell International. Basically, it is a tender-based system, and the GPS satellites are made as per the tender. So Rockwell International was the first one to do it, and then thereafter the Boeing came into picture, and then Lockheed Martin came, and again it went to Boeing, and currently the latest satellites are being built by the Lockheed Martin. So these all GPS satellites, they are functioning in a common coordinate system, that is WG34, and they have a master control station at the Colorado Springs. So this is the basic design, where we have 6 orbits. Each orbit is having minimum 4 satellites in case of Navistar GPS, making a count of 24 minimum. However, as the dependency on the GPS satellites is large, a large number of satellite redundancy is kept. About 30 satellites are there nowadays, 32 satellites which are functioning. Some are kept as spares, and these orbits are 12 hourly orbits, and on the ground they are visible from any of the stations ranging from 4 to 5 hours. So these are the ground stations, 5 basic stations which were initially made. Later on, new stations have been added into it, but these 5 are the configuration 0, we can say, that was most important base station, that is at the Colorado Springs, Hawaiian Islands, Ascension Islands, Diego Garcia, and Quezon. Thereafter, a lot of other stations have come. So currently there are 16 monitoring stations which are there across the globe, out of which 5 are the basic ones which I have shown in the previous slide. So out of these 16, 6 are owned by the Air Force and 10 are taken care by the National Geospatial Intelligence Agency. So these 6 stations are there, which form the part of the ground segment. Okay, so space segment consists of the satellites, ground segment consists of the ground stations. So the master control station is again at the Colorado Springs, and it collects all the data from the monitoring stations, which collect the data from their satellites with which it is in touch. It collects all the pseudo-range data, broadcast ephemeris data, and the parameters required for satellite clock modeling. And all these data sets are transmitted to the master control station. There, the corrections are carried out into the all the observations. Basically, in the surveying, we represent the distance as a range, but in GPS we call it a pseudo range. Pseudo means false. So basically, in order to represent that there are certain errors in the computation of distance, we call it a pseudo range instead of the range. A similar setup is there for the Russian system also in the ground segment, that various stations are there in the ground. They also have various frequencies. So each satellite used to have different frequencies, but then they used to have some RFI effects where the interference was observed in the signals. So thereafter they reduced their frequencies from 24 to 12. So they positioned the satellite opposite to each other across the globe. So that is called the opposite location on the satellite, geographically opposite. So what happens when the receivers function, they do not receive the signals from two satellites which are operating in the same frequency. Whereas in case of the US system, this is little simpler, where we are using initially L1 and L2 frequency only. So that also you will see in detail. So after the satellite segment and the ground segment, we come to the third segment, that is the user segment. So it includes the users like us, which are functioning and utilizing the GPS or the GNSS services across the globe, in the ocean or on the land or in the air or in the space. Okay, so everywhere the GNSS services are being utilized currently, and these all users, they fall into the category of user segment. So these three segments are there under any category of satellite systems which are developed by various countries. Now, why we are using GPS? Basically because it is weather independent, and very critically from surveying point of view, it do not require line of sight. See, if we are using total station, theodolite, tachymeter, we need a clear line of sight, because we have a reflector or a staff reading which need to be taken on the other side of the equipment. So if there is any hindrance between the two, we cannot take the measurement. But in case of the GPS, the signals are directly coming to the GPS from the space, where we have the GPS satellite. So we do not require a clear line of sight on the ground. So that is one advantage in case of GPS. And then this GPS or the GNSS takes care of the shape of the Earth also. So it provides us a geodetic accuracy. It uses the spherical trigonometry and provides us very accurate position on the Earth. And it can provide it in the anytime. It can work in day or night also, and it's very economical. And this is the first system which provides positioning in a common coordinate system all over the globe, with wide range of applications and very competitively priced. And we require very less manpower in case of the GPS. Okay, so that was the basic theoretical component. Now we will come to the point that how the GPS satellites are functioning. So that can be explained in 5 easy steps actually. If you see the diagram, basically this is the one-way ranging signal. So signals are only coming from the satellite to the receiver. Receiver do not send any signals back to the satellite. So these signals are coming to the receiver. The signal starts from the satellite at time t1 and reaches the receiver at time t2. So t2 minus t1 provides us the distance traveled by the signal, and this delta t multiplied by the speed of light provides us the difference or the distance between the satellite and the receiver. So that we represent as the P, that is the pseudo range. So now we know the coordinates of the satellite from the ephemeris data which was received by the receiver, and we know the pseudo range also. So by using this coordinate of the satellite and the pseudo range, a sphere can be generated around the satellite position and the receiver is somewhere on the satellite. So, but this is too much of the uncertainty in positioning using one satellite. So from one satellite we cannot get the solution. So when we intersect two satellites, spheres which we are generating using the pseudo ranges, it intersects into a circle. So now the receiver is somewhere on this circle. And when we intersect the third sphere from the third satellite, so we get 2 points at the intersecting point. So either of these 2 points is the actual position of the receiver. One is a real solution, another is the vague solution. Okay. So minimum satellites which are required for positioning is 3, considering the static parameters otherwise. And considering that we have 3 unknowns, that is latitude, longitude and height. But actually what happens that we have another 4th unknown, that is the clock bias, and that emerges because in the satellites we have atomic clocks in case of GPS, whereas in the receiver we have quartz clock. So the precision and accuracy of the 2 clocks is different and they need some sort of synchronization. So we have the 4th unknown, that is called the clock bias, and because of that the minimum number of satellite signals which is required becomes 4 instead of 3. So now we require minimum 4 satellites to provide signal to the receiver, providing the accuracy what is desired. So we have 4 equation requirement for resolving the 4 unknowns: latitude, longitude, height, and then the clock bias. Now in this, timing is very important because we are talking about the speed of light. So when we are computing the distance between satellite and the receiver, any error in the clock can cause a high damage in computation of the positioning. So what we can see is if we are having an error of 1/10 second, it can result into an error of 30,000 kilometers. So practically we are out of Earth. Okay. And even if we have a microsecond error in our computation, then also we have a 300-meter error. So that is also not acceptable. So we need something better than nanosecond, because even in nanosecond also, that kind of accuracy in timing, what will happen? We will have an error of the order of 0.3 meter, that is 30 centimeter, and that 30 centimeter error is also not acceptable in many applications, such as where we are talking about the urban mapping and the water resources. So 30 meter is also a very big error there. So we need better than that. So we are having timing accuracies of the order of 1 in 10 to the power 13 or 1 in 10 to the power 14 using the hydrogen measure atomic clocks or rubidium or cesium atomic clocks. Okay, so let us have a small query session now. So what we have discussed is the Lorentz system. So maybe for a minute you can have a look at these questions and think about it. What are the correct answers for these? Okay, the first question was on the counterpart system of Lorentz, so that we have already seen that which was the system. So Chaika was the counterpart. What is Who developed the Galileo? So Galileo is developed by European Union. GPS is based on one-way ranging system or two-way ranging system. So as just now I have talked, it is the one-way ranging system. Then GLONASS initially has been functioning on the FDMA system, and currently it is working on FDMA as well as CDMA system. Okay, and the counterpart of Alpha, which is the global terrestrial based positioning system, the counterpart is the Omega system. Then BDO is developed by China. The accumulated drift of receiver clock is called the clock bias, which is the fourth unknown, as just we have discussed in the previous slides. And for positioning, we require minimum 4 number of satellites, because as we have seen in the previous slide, we have 4 unknowns actually. We have unknown as X, Y, Z, and the clock bias B. So with the help of the 4 satellite signals, we make these 4 pseudo-range equations, P1, P2, P3, and P4. So using the C delta T, we know P1, P2, P3, and P4, and X1, Y1, Z1, that is the coordinates for the first satellite. They are known from the ephemeris data of the first satellite, and similarly the second satellite coordinates, third satellite coordinates, and the fourth satellite coordinates are also known from the ephemeris data. So what remains in this 4 equations is X, Y, Z, and B. So X, Y, Z are the position of the receiver, and B is the clock bias. So using these 4 equations, we can resolve the position. As the entire system is dynamic, so when you operate the GPS, you see that the values are fluctuating or changing continuously because all the satellites are in motion, Earth is in motion, and in real time the solution is being computed by the engine which is working in the background, either in the GPS or the smartphone or the server providing the assisted GPS or the assisted GNSS services. The equations are non-linear, however they are easily solved by using the computers nowadays. Now coming to the timing actually, so the time which we are using is the International Atomic Time. This is different from the UTC time, from the GPS time by about 13 leap second. And the GPS time actually is computed from the first Sunday in 1980. That was the 6th January. So these atomic clocks are highly accurate, providing us accuracy of the order of 1/10 to the power 13 or even better. So now after this, we will come to the GPS signal structure, which is one of the very important part. So we are using the L1 and L2 carrier waves at frequency of 1575 and 1227 megahertz. And there are different type of codes, which is called CA code, course acquisition code, and P code, which are modulated on the L1 carrier wave, and on the L2 carrier wave, P code is only modulated. So this is the basic system. Like in the initial case, I told 5 ground stations were there, and then later new ground stations were added, and the final number is 16. So similarly, for the GPS also, initially this L1 and L2 were there, and the codes which were there were the C code and the P code, and P code is the encrypted code, so it is called the Y code. Besides the CA code and P code, there is a 50 bit per second satellite message also, which is also coming to the receiver, and it provides the almanac, that is the coordinates of the satellites, and it includes for all the satellites which are there in the range of the ground station or not in the range of the ground station or the receiver. All the constellation coordinates will be there, whereas the ephemeris represent the position or the instantaneous position of the satellites in a particular orbit. So all these things are downloaded in the receiver, and the fundamental frequency for GPS is 10.23 megahertz. Basically, the frequencies range in the bandwidth which basically from the range 1.1 gigahertz to 1.6 gigahertz. For the GLONASS, fundamental frequency is 5 gigahertz, which is almost half of the fundamental frequency which is being used in the Navistar GPS. Now, besides this L1 and L2, there are other frequencies also like L3 and L4, which are used by US agencies for finding atomic flash or nuclear detonation anywhere on the Earth. Then thereafter, L5 frequency is also added from the block 2F, and it provides a new category of signals, I5 and Q5. Ports are there, which are used for the indoor applications, safety of life operations, and have anti-jamming characteristics also. Besides this L1C and L2C ports, they are also added recently for the civilian and the military applications. However, they have to be fully operationalized. L1C and L2C are currently in the pre-operational testing phase. However, L1C has completed enough number of satellites are there in case of the L2C. Okay, but L1C is there in the third block. So we have only 4 satellites in third block. So L1C do not have sufficient number currently. But both L1C and L2C are in the pre-operational testing phase. So these are the new civilian satellites, L2C, L5 and L1C. Currently what we are using is the phase solution. So we are able to use L1 and L2 both carrier waves, providing us a phase solution providing centimeter to millimeter level of accuracies. However, if we will use the code-based solutions, then the accuracy what we get is of the order of meters only. Okay, so now these L2C signals are the new signals which are there to provide high accuracy for the civilian systems also, because in case of the defense, the P code is overlaid on the or modulated on L1 and L2, both the carrier waves. So unnecessary corrections can be done for them. But for the civilian operations, the CA code is only there on the L1. So that is why this L2C and L1C are being added now to provide higher accuracy, and the strengths of L1, L2C, L2, L5, L1C, all of them, the strengths of signals have been increased to provide anti-jamming features and indoor services to the users. P code is a quite long signal while having 2.35 into 10 to the power 14 bits. It has a time period of 266 days. This is a quite complex signal which is being utilized for the strategic operations of the US. And this is an encrypted, so it is called, after encryption, it is called Y code. And this encryption is referred as a anti-spoofing phenomena. Whereas L1C is a very small code, and its size is only 1023 bit in case of GPS and 511 bit in case of GLONASS. So this is known as a gold code, and it is quite small with a very small time period, and it is used for the civilian applications. So these codes are used, and these are now being augmented by the L1C and L2C signals for getting higher accuracy for the civilian operations. So today we will stop here, and now we will have the query session. So you can ask various queries what we have pertaining to today's lecture, and then we will continue hereafter tomorrow. So you can ask questions, either you can unmute yourself and you can ask, or you can send your queries through the chat.